Hello, everyone, and welcome to Calculus. Today we'll be studying the mean value theorem. So the mean value theorem, which is generally abbreviated as just MVT, states that if y is equal to f of x is continuous on every point from the closed interval a to b and differentiable, so remember that means no cusps, no corners, no points of discontinuity, if it's differentiable at every point on its interior, then there is at least one number between a and b at which f of b minus f of a over b minus a is equal to the derivative at point C. What is this saying? This is just saying that the average slope is equal to the slope at a point. So on my graph, the average slope from A to B would just be this. Sometimes the slope is steeper. Sometimes the slope is about the same. Sometimes the slope is not even in the same direction, right? This is a negative slope. And then it's positive again. But if I actually knew all these little slopes along the way and I averaged them together, I would get this number right here, whatever the slope is of the average between the 2 points. The question we want to say, or what the mean value theorem says, is at some point along the curve actually has the value which is the same as the average value. So like we kind of pointed out before, maybe right there, and maybe again right there. Another way to think about it is that the difference quotient is the average rate of change, while the derivative is the instantaneous rate of change. So let me give you a little example. If a car is accelerating from 0 and it takes 8 seconds for it to go 352 feet. So here's the time, here's 8 seconds, here's the feet, the distance, and it gets to 352 feet. You know, it can't go really fast in the beginning. You've tried to pull away from a stoplight. It takes a couple seconds for your car to get going, but then you pick up speed really fast. But it's definitely not linear. So the average would just be this. So in this case, if you actually did 352 divided by 8, you would get 44 feet per second. Just to give you a sense of what that is, that's 30 miles per hour. So at some point during the acceleration, the speedometer actually was 30 miles per hour. It wasn't here. The second you took off, it wasn't 30. And by the end of the 8 seconds, you could be going well faster than the 30 miles per hour, right? 8 seconds, you can definitely get up to like 50 or 55. But at some point, your average was 30. So at some point, you must have actually been going 30. That's the mean value theorem. It is not to be confused with the intermediate value theorem. Remember this one, IVT? It's easy to do, but the mean value theorem has to do with the average slope being equal to the slope at a point. The intermediate value is just its y value. So at some point you were 0 feet, and then you got up to 352 feet away. At some point you were 350 feet away. At some point you were 102 feet away. That's the intermediate value. If you go from 0 to 352, at some point you were at 100 or you were at 87. You're at all those different points. That's the intermediate value. But that also has to have a continuous function for that to work. So mean value, the word mean means average. So that's how you can remember it, that this has to do with the average velocity versus the instantaneous velocity. Let's do some actual problems, and it hopefully will clear anything up. For each of the following functions on the indicated intervals, determine whether or not the mean value theorem applies. So remember, there's two conditions. It has to be continuous and it has to be differentiable. If it does apply, find the value where the mean value or the average value is attained. So I'm just going to draw that, I'm going to draw it. So it's a cubic function that's been moved upward. I don't really need to draw too much of it. I kind of want to draw these 3 points because it helps me picture it, but I do need to get from 1 to 2. And at 2, it's going to be all the way up there at 9. So 2, 9. So just to put it into steps for you, step 1, find the average value, which is just the slope. Okay? Sub part 1, A, you need 2 points. So in this case, 1 comma, because we're on the interval from 1 to 2. So 1, 2 is a point, and then 2, 9 is a point. B, use the slope formula. So 9 minus 2 over 2 minus 1 is equal to 7. Step 2, find the derivative. In this case, y prime is equal to 3x squared plus 0. Step 3, set them equal. So you're going to figure out where the average value is equal to the instantaneous value. So for us, 7 at some point must be equal to 3x squared. Remember that 3x squared is a formula for the slope at any point. It'll tell me the slope anywhere. But I'm saying, is there a place where the slope is 7? Because I know that that's the slope of this line. This slope is 7. Sometimes it's steeper than 7. Sometimes it's not as steep as 7, but somewhere it actually has a steepness of 7. Where is that spot? Divide both sides by 3. X is equal to plus or minus the square root of 7/3. So if you were going to have a step 4, it would be answer in the interval. So in this case, we're on the interval 1 to 2, so the negative would not apply. So where does the mean value, where is it obtained? At the square root of 7/3. Okay? If you rationalize the denominator, square root of 21 over 3. Same thing. Okay. So number 2 is on here because I have a slightly embarrassing story. The first time I ever saw this problem, I immediately simplified it to, the square root of x squared is just x plus 1, which is a line. And of course, I got the wrong answer. And it took me forever to figure it out. And I confess I finally asked another teacher, and I was embarrassed that they said, well, the first step is to simplify the square root of x squared, which is the absolute value of x. And I was like, oh, yeah, duh. So be warned, mistake I made, which is, so if you have, think about it, if you have the square root of 3 squared, you get the square root of 9, which is 3. So in this case, the square root of x squared did come out to be x. But if you have the square root of negative 3 squared, so x is equal to negative 3, then you get the square root of 9, which comes out to be 3. So did the square root of x squared come out to be x? No. Once you square it, that makes it positive. And when you take the square root, you're going to get positive. So the square root of x squared will actually come out to be the absolute value of x. So as always, I'm going to graph it. It's an absolute value that's been moved up 1, so it's some kind of v. On the interval -1 to 1, -1, to 1. Is there an average value? Yes. I don't even need to find the two. I mean, you can find the 2 points. It's 1, 2, and negative 1, 2. But if you found the slope, you could use the formula if you want to, but it's clearly 0. So is there some point where the derivative is equal to 0? No. The derivative is negative 1, and then the derivative is positive 1. We don't know how to take the derivative of an absolute value function. We've never done it because absolute value functions are just lines. You can just see their slope. So there's no reason to learn how to take the derivative of an absolute value function. So what happened on this one? Step 1, well, not our step 1, but like before you even start, for each of the following functions, determine whether or not the mean value theorem applies. There's 2 things. It has to be continuous and differentiable. So since this is not differentiable at x is equal to 0, the mean value theorem does not apply. Okay, so before you do these problems, you'll be happy to know that when you go to do your homework, there's a whole bunch of them where you can just write the mean value theorem does not apply because, make sure you tell me why. On your test, I will ask, is it because there's a cusp or a corner or a point of discontinuity? There has to be a reason why the mean value theorem doesn't apply. Either it's not continuous or it's not differentiable. So if you would like to do these next few on your own, that's what I would have you do if you were in class. But of course, I am going to do them for you. So for number 3, sometimes you'll see that there's 2 intervals there. I want you to do the mean value theorem on both of them. Okay, I will quick write up the answers for people that are just going to try and do them on their own. Mean value theorem doesn't apply on that one. X is equal to the square root of 3 minus 2. On this one, x is equal to 3.764. On this one, it does not apply. On this one, x is equal to 0. On number 6, mean the value theorem does not apply. It does not apply on the first part of number 7. And on this one, the slope is equal to 1 at every point. All right, so if you wanted to write down those answers or screenshot them, there you go. All right, let's do them. So you know I'm always going to make the graph. And there's an asymptote at -2. There's also an asymptote at 0 because the numerator is x to the 0, and then 0x to the first. So when you compare like exponents, the first linear ones, it's 0 over 1. So there's something there. And the y-intercept, if x is 0, is 1.5. So now I know it goes like this, which means the other one does something like this. So on the interval from -3, 1, 2, 3, so from here to here, there's a point of discontinuity. So the mean value theorem does not apply. Make sure you write why. Because f of x is not continuous over the interval. Hence my giving you another interval. So we don't have to redraw the graph. So now my interval is from -1, which is right here, to 1, which is right here. So on that interval, this function is continuous, so I can do the mean value theorem. I can find that slope. So remember, step 1 is to actually find the slope. So I need 2 points. -1 is 2. Is that right? I didn't actually plug it in. I just kind of guessed at that. But if I plug in -1 in here, it's actually 3. 1, 2, a little higher than I drew it. And at 1, it's going to be 1. So my slope is 1 minus 3 over 1 minus a -1. Negative 2 over 2 is negative 1. Step 2, we're going to find the derivative. So my original equation is 3 over x plus 2, but I personally think when the top is a monomial, it's really easy to just do it this way. Y prime is negative 3 over x, or times x plus 2 to the negative 2 times 1. So my derivative is negative 3 over x plus 2 squared. And step 3, set them equal to each other. Negative 1 is equal to negative 3 over x plus 2 squared. So I'm going to make both sides positive. I'm going to move the square to the other side by multiplying, clearing the fraction. And then I have x plus 2 is equal to plus or minus the square root of 3. X is equal to negative 2 plus or minus the square root of 3. Only one of these can be in that interval from negative 1 to 2. Remember, the last step is to check your actual answer. Negative 2 minus the square root of 3 is definitely over here. And it does make sense that it produced two answers because there is, whatever this slope is, negative 1, that's the slope right there between those 2 points. It does obtain the slope of negative 1 over on that side too, but I just want to know on this interval. So my final answer is x is equal to negative 2 plus the square root of 3, which is about 1.7. So this would give me negative 0.3. So apparently it obtains it right somewhere like right there. Okay. All right. Next one, number 4. So this isn't a graph that you're super familiar with, but it is an easy graph to make because it's 0, 0, 1, 1. 1 to the anything is still 1. And negative 1 is also going to be 1 because negative 1 squared is 1, and then cube root is still 1. And then the reason it goes to 8 is because that's just an easy number to do. If you were figuring this out at 8 to the 2/3 means cube root of 8 squared. So cube root of 8 is 2, and 2 squared is 4. 1, 2, 3, 4, and 8. So it looks like this, where this is the point 8, 4. And then it does the same thing on the other side. Negative 8, 4. It's an even function, but it is not differentiable. Remember that this is a very big word, differentiable. Remember that this is called a cusp. When something comes in like that and then goes back out like that, that's called a cusp. So instead, we're going to limit it to 1 to 8. So the mean value theorem does not apply on that interval. So obviously, I want you to do the problem. So I switched to this interval right here. Let's draw that. So from 1 to 8, I'm going to find that slope, step 1. M is, this is the point 1, 1. So 4 minus 1 over 8 minus 1 is 3/7. Step 2, find the derivative. Because what this is saying is that this is the average slope. Somewhere does it actually have that slope? Yeah, not right there, right? Not right there. Maybe, I don't know. It's a very fine line, but somewhere on there, we're about to find it. So the derivative is 2/3 x to the negative 1/3, which is 2 over 3 cube roots of x. So I'm going to set them equal to each other for my step 3. 3 over 7 is equal to 2 over 3 cube roots of x. I'm going to clear my fraction by multiplying both sides by the 7 and both sides by the 3x to the 1/3. I keep changing my mind about how I want that to look. It doesn't really matter. Whatever you're most comfortable with, you should be writing. My 7's cancel, and I get 9x to the 1/3 is equal to, this all cancels, and I get 14. x to the 1/3 is equal to 14 over 9. And I can finish that off by cubing it. So x is equal to 14 divided by 9 to the third, which is 3.764. So let's think about that. 1, 2, 3, 4. So somewhere right there, that slope is the same as the average slope. And it should look right. You should feel good about it being in the interval. Number 5. I'm hoping that you're going to start to recognize this problem. So in case you don't, let me show you how to start to recognize it. I'm going to square both sides. I was about to go, tell me when you see it, like you can talk to me. And then I add x squared to both sides. See it yet? It's a circle. But it's actually not quite a circle, because if you were to start with the circle and then subtract x squared from both sides and then square root both sides, you would actually get plus or minus. We only have plus. So it's a half circle. Okay? This graph from -1, it's a circle of radius 1 to 1. It is a function I'd like you to start to recognize. A number, especially a perfect square number, minus x squared. This represents a half circle. So it looks like this. So notice that they have open circles there. So let's go back, and this one's kind of important. We do have to go back and read what it says in the original. It says that it has to be continuous, which the half circle is, at every point on the closed interval. So even though ours is an open interval, it's still, is it continuous if this was closed? It would be continuous. So it is continuous on the closed interval, even though they don't actually want us to find, like to actually graph that point. It would have been continuous. And then, so it's continuous on the closed interval and differentiable at every point of its interior. That's the point that's really important to me. This is not differentiable right here. At 1, if you were to actually take the derivative, y prime would be equal to 1/2 1 minus x squared to the -1/2 times -2x. The derivative would actually be -x over the square root of 1 minus x squared. It would not have a derivative at 1, because think about it, right there on the circle, what happens right at the side there? It's completely vertical. Its slope is undefined. So that's why it's a parenthesis here, because they don't want you to have it not be differentiable right at that point. But does that mean that the mean value theorem doesn't apply? Not at all, because they didn't choose to include that. They wanted to stick to it's differentiable on the interval. So it is differentiable, and we can figure out the slope. I mean, we could do it the long way with the formula. 1, 0, -1, 0. The slope would be 0 minus 0 over 1 minus a -1. But I think you can just look at it, right? The slope between these 2 points is definitely 0. Where does it obtain 0? Definitely right here. Do you have to do steps 1, 2, 3? Find the slope, find the derivative, set them equal? Well, I did find the derivative only because I was trying to explain to you how it's not differentiable at -1 and 1. But if you can just look at a problem and see it, go for it. So where does this obtain the mean value? At x is equal to 0. Between the two endpoints, you get a slope of 0. This represents the average slope. Now think about that. It's positive, less positive, less positive, and then it's negative, negative, more negative. All these positive slopes cancel out all these negative slopes. That's why the average is 0. And at some point, does it have a slope of 0? right at the top. All right, I hope mean value theorem is starting to make sense, but we do have two more to help you firm it up here. So I know this is just your favorite, making a piecewise function. So this is a parabola that's going facing up, and it's been moved up 1. But I only want this parabola greater than 1. So the most important point to me to plot is 1, which is 1, 2. But if you can kind of picture it coming in like this, it'll help you draw the rest of it. So you can't actually leave that there, but that's how that would look. Okay. And then the other one is going to be x cubed plus 3. So a cubic graph would look like this. This is an open circle because it's not actually equal to 1, but you still need to plot that point. So at 1, it's up here at 4, and it comes up like that. I'm trying to fill that in. So the mean value theorem does not apply because the graph is not continuous. You always have to check for continuity and differentiability. Next one. I hope you guys are seeing that all this graphing I've forced you to do is paying off. So this is an absolute value function, which means it's a v. It's been moved to the right 1 on the interval from 0 to 4. 1, 2, 3, 4. It does have a slope, but that is not the average slope because it has a slope of -1 and then it has a slope of +1. But this slope doesn't necessarily mean that it's somewhere it obtains that slope. In fact, I can see that it doesn't. It's either this, -1, or it's +1. It is never going to be that slope. That's because the mean value theorem only applies if it is both differentiable and continuous. So you always have to state why this is not enough of an answer, because f of x is not differentiable at x is equal to 1. Because there is a, what do we call that? Corner, not a cusp. This one's called a corner. So they say, all right, well then just do it from 2 to 6. Well, from 2 to 6, the slope is always 1. There's no point that you can find for me. You can't say, oh, the mean value theorem applies and it obtains its average at a certain point. It obtains the average at every point. The slope is always 1. So you're not really going to get a mean value theorem question that's like this, but I wanted you to see how it worked. Okay, so let's do a little application problem here. So a marathoner ran the 26.2 New York City Marathon in 2.2 hours. So let's make a graph of that. Here's the time, and here's the distance. So we know that they reached a distance of 26.2, and they did it in a time of 2.2 hours. So I know that at time 0, they hadn't gone anywhere yet, and at 2.2, they did that. This represents the average pace. Is that what the runner did? I'm sure they did not, right? They took off like a shot, and then they leveled it off, and then maybe they followed that average pace for quite a while. But then at the end, they really sped up, right? Or maybe they were dog tired, but let's just assume that they had like a little burst of energy there at the end. All these numbers, if you average them together, whatever they did, they would average to that blue line. So let's find out what their average pace was. So this is the point 2.2, 26.2. Step 1 is always define the slope, which requires 2 points. 26.2 divided minus 0. I don't know if you need that or not. 2.2 minus 0 is equal to 11.9. So miles per hour is the average pace. So by the mean value theorem, at some point, the marathoner was running 11.9 miles per hour. That's amazing. Okay, that was their average pace. They were probably going faster than that in the beginning. At some point, they might have been going slower. It's 2 hours. They might have stopped at some point for one of those little quick drinks and maybe running faster at the end. But that was their average pace. I can't actually figure out when they were doing that because I don't have a function and a derivative. So I can't really apply the mean value theorem. But I do know that at some point it was happening. I just can't figure out where. But that's not their question. Their question says, show that at least twice the marathoner was running at exactly 11 miles per hour. So this question is actually intermediate value theorem. I put it on here because I just want to make sure that you're not going to confuse the two issues. By the mean value theorem, I know at some point they were running 11.9. The reason I know that they were running at 11 is because they started at velocity, I guess we'll call it. Velocity is equal to 0 and reached velocity is equal to 11.9 miles per hour. So by the intermediate value theorem, since it is a continuous measure, right? You can't like jump from going 1 mile an hour to 3 miles an hour. It's continuous. At some point, I like how I'm writing right on top of each other. At some point, he or she was going 11 miles per hour. If you go from 0 to 11.9, at some point you were going 11. Why is it twice? Well, because they also had to slow back down, right? Students have argued with me in the past. No, maybe they never, they just crossed the finish line. They got to that average and they never slowed back down. All right, so I'm not going to argue that point, but definitely at least once, they were definitely at 0, and if this was their average pace, then they must have at some point been 11. But that's intermediate value theorem, so make sure you understand the difference. All right, so you're gonna like this last little part. It's easy, and it looks awful though, doesn't it? So here's what I really want to tell you. I want you guys to go to college and not look at complicated math things and say, oh, I don't get this at all. When you see something complicated, you need to tell yourself, I can understand this. Because honestly, you can. And I swear, I think they get paid the big bucks just to try and confuse poor kids. All right, so I'm gonna give this to you, and then I'm gonna put it into plain English, and you're gonna laugh at how easy it is. The mean value theorem is used to derive the following corollaries: increasing and decreasing functions. Let f of x be continuous from A to B and differentiable. So it's no cusps, no corners. If the derivative is greater than 0, which means slope is positive, then the function is increasing. What? We already knew that. They literally are giving credit to the mean value theorem for making this hypothesis. They're saying if the derivative is positive, then the function is increasing. This is totally obvious. So don't let the big words throw you, big fancy words throw you. There's not actually any big words. If the derivative is less than 0, so if the slope is negative, then the function is decreasing. Well, of course it is. When the slope is negative, the function is going down. There you go. That's corollary number 1. Functions where the derivative is equal to 0 are constant. So if the derivative is 0, which means if the slope is 0, then the function must be constant, which we also knew. This must be a line, like y is equal to 3, right? And if the derivative is equal to 0 at every single point, then there must be a constant c for which f of x is equal to c. Yeah, I got that, right? Y is equal to 3. So I just love this. I just love that somebody decided to make these things called corollaries when they're just so obvious. All right, here's another one. Functions with the same derivative differ by a constant. So they're saying if f prime is equal to g prime at every single point, then there's a constant such that f of x is equal to g of x plus c. All right, I know that sounds confusing, but again, I'm going to show you that it's really not. So you have a function, f of x, and then you have another function, g of x, and every single point, the derivative is the same. So when this one has a slope there, mine has a slope there. When this one has a slope like this, mine has a slope like this. When this one has a slope of 0, mine has a slope of 0. When this one has a slope here, mine has a slope here. It's literally doing the same thing. Whatever you do, I'm going to do. What do I see? I see that g of x, if you just add c, you'll get f of x, or vice versa. I guess I went up. So for me, g of x is f of x plus c, which is backwards from what they said. But you get the point. The point is that f of x and g of x are pretty much the same function. They've just been moved up or down from each other. Okay? But they made that sound so complicated, didn't they? So when you guys see something next year, and even if I didn't teach it to you, just say to yourself, you know what? I'm going to draw a picture. I'm going to try and analyze what they're saying. And I bet I'm smart enough to figure it out, because you are smart enough to figure it out. So please don't let college intimidate you. These are literally the examples from the book that came with these corollaries. You're going to love this. Determine where the function y is, I'm just laughing. Determine where the function y is equal to x squared is increasing and where it's decreasing. Okay. So you've just done all this hard calculus. We've done modeling and optimization and related rates and derivatives of inverse trigonometric functions. And now they want to know where this is increasing or decreasing. So it is increasing from 0 to infinity, and it is decreasing from negative infinity to 0. On number 2, again, they want to know where it's increasing or decreasing. We know that to find increasing or decreasing, I mean, on number 1, I just drew it. But on number 2, we can actually find the derivative, which is 3x squared minus 4. I couldn't have done this one in my head. I don't know those points well enough. So I take the derivative and I set it equal to 0. And I get 4/3 is equal to x squared. So x is equal to plus or minus the square root of 4/3, which is plus or minus 2 square roots of 3 over 3, which is nice and simplified, but it doesn't really help me find anything. But negative 2 square roots of 3 over 3, and then positive 2 square roots of 3 over 3. Luckily, remember, no matter how complicated these points are, you can still plug in something like 100, and that's still going to work. If you plug 100 into this equation, it's going to be positive. A nice easy one between a negative and a positive is 0. If you plug a 0 into your derivative equation, you'll get a negative. And if you plug in, again, 100, negative 100, it'll still come out to be positive because it's being squared. But you knew that, didn't you? This is a cubic function. You knew it was going to be rising, falling, rising, rising, falling, rising. But you did need the derivative to find these points. So this is the corollary for the mean value theorem, that if the derivative is greater than 0, so that's how you can determine increasing and decreasing. So it is increasing from negative infinity to And I don't care if you write it as negative square root of 4/3, or if you write it as 2 square roots of 3 over 3. This is not what I'm being fussy about. I do want you to get the intervals, though. And it's decreasing from negative 2 square roots of 3 over 3 to 2 square roots of 3 over 3. Okay, so we've already done this in past sections, but it's coming up again because it's a corollary to the mean value theorem. All right, the third corollary. So find a function whose derivative is sine of x. So you're working backwards here. If the derivative is sine of x, what must the original function have been? Careful now, think hard. Did you say cosine of x? Because that's wrong. Negative cosine of x, right? Because the derivative of cosine is actually negative sine. So it must have started out as a negative sine. But now it says, and whose graph passes through the point 0, 2. Well, we know that negative cosine actually passes, or starts, I should say, down here at negative 1. That's what negative cosine looks like. So how would it get to 0, 2? If it had been moved up 1, 2, 3. So this must be the original function. But honestly, anything with this constant at the end lets it go through that point. But no matter what this constant is, it's going to have a derivative of sine of x. This little corollary is like a little teaser, little trailer for the next unit. This is what we're going to be doing on the next unit, is derivatives backwards. All right, that is what this last page is going to be, is pretty much doing derivatives backwards. So a function capital F, this is the notation that they often use when you go in the opposite direction, is the antiderivative of the function f of x. So if you think about it, kind of like our SVA, if this is your main function, the one when you'd go backwards is going to be capital F of x, and the derivative when you go forward is f prime of x. Will it always stick to these? Definitely not. But just like SVA, this is the main pattern for it, and then they'll keep changing up all the names. So find the velocity and position functions of a body falling freely from a height of 60 meters under each of the following conditions. So look, they started with the acceleration. So here's the acceleration, negative 9.8 meters per second squared. If you want to know the velocity, what would the velocity had to have been in order to get an acceleration of that? It must have been negative 9.8 with the t, because the derivative of this would have just been negative 9.8. But could there have been a number there? There definitely could have. This is what this third corollary is trying so fancy to say, that you know the derivative, but there could have been a number there. So do we have anything that tells us what that number is? Yes. The body falls from rest. That means at time is equal to 0, the velocity was equal to 0. So 0 is equal to negative 9.8 at time 0 plus c. So c is equal to 0. So c was actually equal to 0, so my velocity is just negative 9.8 t. That's the velocity. Then it says find the position function. So now I'm going to go up again. I have the velocity. So this one's a little harder now. What must the distance, or they call it the position function, have been that produced this velocity? So normally I'd make you stumble over it and think about it for a few minutes, but of course, you're just watching a video, so you're probably just going to wait for me anyway. 4.9 t squared. Because if you were to take the derivative, you would do 2 times negative 4.9 and get negative 9.8, and then you'd make it t to the first. But again, there could have been something there. So you always need an actual point to plug in. So do we know anything? Do we know the height at any time t? We do. It says that it's falling from a height of 60 meters. So at t is equal to 0, the distance, or in this case, the height, is equal to 60. So S of t, or I should say S of 0, is equal to 60. So 60 is equal to negative 4.90 squared plus c. So what does that mean that c is? C is equal to 60. So my final answer is S of t is equal to negative 4.9 t squared plus 60. That is the velocity and position function for part A. You should try to do part B on your own. I'm going to give you the two answers over here. Velocity is negative 9.8 t minus 1, and S is equal to negative 4.9 t squared minus t plus 60. Hopefully you're doing B on your own. If you're not, then I'll do them for you. So it starts out the same way. The acceleration is negative 9.8. So to do the antiderivative, so I'm trying to figure out what made the derivative be negative 9.8. It's negative 9.8 t to the first. And all you have to do is go backwards to check that. 1 times negative 9.8, and then you lose the t. So that definitely works. But there could have been a number here because that derivative would have been 0, so it still works. So you need to always plug in a known point to find c. In this case, I know that the velocity it says the body is propelled downwards. That means somebody's throwing it with an initial velocity of 1 meter per second. So at time 0, it already has a velocity of 1. So 1 is equal to negative 9.8 times 0 plus c. This goes away so nicely, so c is equal to 1. My velocity equation is negative 9.8 t plus 1. Oh, sorry, it's propelled. I'm looking at my answer. It's propelled downward, so it has a downward velocity. So the velocity is negative 1. And now I'm going to do my S equation. Same thing. I've got to do the antiderivative. I've got to figure out what would have made negative 9.8 t negative 4.9 t squared. So the trick for that is to raise the power by 1. So it was t to the first, now it's going to be t squared, and then just divide by your new power. That always works. When we do the whole entire unit on integration, that's the actual name for anti-differentiation, is integration. So when we do integration, we'll learn all the tricks. And then what must this one have been? Just minus t. Think about that. The derivative of minus t would be negative 1. And there could have been a constant. So now, again, we're going to plug in a known point. Is there any point that we know? Yes, it says, remember, part B is still part of the original equation. So it says that it's falling from a height of 60 meters. So we know that S of 0 at time 0, it was 60 meters high. So 60 is equal to negative 4.90 squared minus 0 plus 60. C is equal to 60. So my S equation is negative 4.9 t squared minus t plus 60. So we're getting our first little taste of anti-differentiation, which is going to be called integration. All right, so it looks like we have 2 problems left. We actually just have 1. This is my challenge problem. If you would like to figure it out, I would love to see the answer on your paper when I check your notes. The goal is to figure out what was the original function that made that derivative. But of course, you can do this one. what is the function where the derivative would just be 2? It must have been 2x. But because it says find all possible functions, you're actually going to write 2x plus c. This is going to be our notation going into the next unit. Okay, f of x is equal to 2x, so the derivative would just be 2, because if c is a constant, it won't matter. But I would love to see who figures this out, not if you just get it on your calculator or a computer. So that's why I'm not going to give you extra credit, because I know you can look it up. Just challenge yourself. See if you can recognize that. What derivative makes a 1 over x minus 1? Okay, so there is a mean value theorem worksheet that you can practice on. And have a great day.